So good afternoon, the last day of the PCIM. Thank you for joining this presentation. My name is Soffer. I'm Chief Strategy Officer within VisIC Technology, specializing in gallium nitride power switches solution, high power. So our focus at VisIC is really for the automotive industry. So we are talking about onboard charger, high power DC to DC and traction inverters. And I believe if we're looking at the industry, these actual pictures describe the complete picture why to move to a newer technology and newer power switches technologies. We could use and we could continue using the very nice and old silicon solution, but really when we are thinking about traction inverters and automotive applications, important thing are losses within the automotive solution. And you can see that moving to wide band gap technology, we could reduce the power losses by half, moving from silicon to silicon carbide, an additional half moving from silicon carbide to gallium nitride technology. And that has a huge impact on the automotive industry, reducing the cost of the car, making the financials of the automotive industry better, and of course, increasing the distance of the car. So what are the numbers behind it? Why we should do this? And what are the reasoning for this to invest in new technologies for the automotive industry? So electrical car market really booming. We are in inflection point moving from internal combustion engine to electrical cars. The assumption is that in 2030, all cars manufacturers will be only producing electrical cars. But the main issue here, and you can see it in the middle, is the cost of the electrical car. It's about 25% higher than internal combustion engine. After 100 years of internal combustion engine, the automotive industry came to a perfection of manufacturing, and this is the reason they could reduce the cost dramatically of the car and definitely live in very low net income profit, which is about 5 to 10%. Analyzing which part in the automotive is the highest cost, we can see that it's the battery and the electrical traction inverters. This is the highest cost. You can see here, this is the battery, and this is the traction inverter. So trying to reduce those has a dramatic impact on the automotive industry. Just think about 25% additional cost. It's about $400 billion that the automotive industry will have to spend manufacturing electrical cars. So this has to be reduced. Battery already came to a very low cost for a kilowatt per hour, and it will continue, but it's starting to flatten. And we have to think about new things, how we can reduce those costs. So up until now, I would say that the government were very supportive, trying to push the electrical car industries into the market, and they subsidized it. They gave benefits. For example, my friend in California actually bought electrical car just because he could drive on the carpool lane and also got tax benefits. I basically live in Israel, didn't receive any tax benefits, and I bought internal combustion engine, unfortunately, although I really want to move to electrical car. So the industry have to think about how to reduce the costs. Those are the main three elements in an electrical car. It's onboard charger, taking AC, turn it to DC in order to charge the battery, and then from the battery, driving the electrical car in order to run the motors. And DC to DC applications. Of course, the inverter, in order to drive the motor, it's the most, I would say, power-hungry element in the car. So really, we have to focus how to reduce the cost and how to reduce the losses of this electrical drive system in order to reduce the battery size, in order to make the car less complex from, for example, weight of the elements that we need in order to cool the systems, and reduce the heat that is generated. And this is the reason moving to new technologies, from silicon to silicon carbide, and then to gallium nitride. Here you can see a graph of switching losses, comparison between the different technologies. And it's really an order of magnitude better switching losses moving from silicon to silicon carbide, and then additional 5 times better moving from silicon to gallium nitride. But how these switching losses really impact the efficiency of the traction inverter systems? So how it's being measured, it's according to the driving cycle. So you can see here a driving cycle sketch. This specifically, it's the WLTP. And you can see on the y-axis, it is the speed of the car, and it's about half an hour drive moving from in-city driving to highway driving between 40 kilometers, stops in traffic lights, and going even up to 130 kilometers per hour. And this is the important part, how we measure the performance of our car. It's over the driving cycle. And trying to measure the performance of the car over the driving cycle will impact the losses from the battery. And you can see here, if we will take silicon, if we will measure it or set it to 100% losses, silicon carbide will give half of it, and gallium nitride additional half of the losses. And this is a major impact on the battery. It is something like $1,000 of the battery, and of course, additional cost from the cooling system. So this is very important in order to reduce the car cost and improve the financials of the OEMs. So why is it so important, the switching losses? This is a graph of describing switching losses compared to conduction losses. In inverter, we do have conduction losses, which will be similar between different technologies because it's being built and designed for a specific current. And when we are designing our inverter, we are designing it for the peak power. So here we took 2 comparisons of up to 150 amp. And you can see in blue, it is the conduction losses. And in brown, something like this, it is the switching losses. Of course, if you will be running the motor always in peak power, conduction losses will be the most significant part of the losses of the inverter. But as I mentioned before, and I saw it, and you can see it here, we are driving not all the time in peak power. Actually, the average, it's about 20 to 30% of the peak power. And this is the reason we should look at those areas here, and in the same thing here in silicon carbide solution. And you can see here now the difference and what is the reason that switching losses are so significant for traction inverters. They are becoming much more significant at those numbers, at 25%. And this is after I convinced you, let's say, that you have to move from silicon carbide to gallium nitride, which was the same thing, moving from silicon to silicon carbide. We wanted to improve performance, and improve performance meaning also reducing the car cost. But we increased the inverter cost with silicon carbide because silicon carbide, of course, it's a much more expensive solution compared to silicon. Next step, next wave, moving to gallium nitride in order to reduce also the inverter cost, as well as improving again the performance. So it's another step of improving performance and getting closer to the silicon cost targets. So after you have been convinced that gallium nitride is the next step for traction inverters, we have two gallium nitride technologies. One of them is depletion mode, D mode, and the other one is enhanced mode, E mode technologies. And what are the main differences between those two technologies? D mode technology, it's usually as a die normally on device. E mode, it's a normally off device, which is quite nice. We, as industry, like the normally off devices. But in order to make a gallium nitride solution a normally off device, you need to add additional process, which is having the layer of the P-GaN. It degrades the performance of the gallium nitride, and you have to do some activities under the gate, or the gate structure is different, which makes it less reliable. When we are talking about automotive, reliability is the most important, and we are thinking about traction inverter, it's even the most important reliability element within the car. So we cannot sacrifice reliability. The EMO technology, it's quite nice, it's good for consumers, for less high power solution, but depletion mode, it's the right technology moving from silicon carbide to gallium nitride in traction inverters, application where reliability is important, but it's not the only thing. Gallium nitride D-mode technology have much higher V threshold, which is giving us design possibilities. We can actually accommodate better the EMIs, things that we can see in electrical, in high power electrical cars and systems. And E-mode, it is a much lower V threshold. So we are talking about reliability, design, and improved performance of D-mode technology compared to E-mode technologies. So I talked about reliability, which is important. And here we can see a comparison done by CPES between the different gallium nitride technologies. You can see here VisIC and additional companies, which I didn't wrote the names of them, but I believe that few of them are E-mode technology, and company C, it's already a D-mode company. So important things to think about is the breakdown voltage of the solution, and you can see that D-mode technology is superior to E-mode technology from breakdown voltage, which is important in order to support spikes in high current, high voltage systems. So after they measured the breakdown voltage, they even took some margin from the breakdown voltage and started to do many, many spikes. This is 1 million spikes in order to check the reliability of the device. And those are the tests of VisIC E-mode technology done by CPES. It's not our test. And you saw a very insignificant degradation after 1 million cycles. So reliability for D-modes is superior on E-mode technology, which is important for traction inverters. So VisIC, what we did is took a D-mode technology, which is a low-cost solution when we are doing gallium nitride over silicon, because the silicon substrate, it's a very low cost. And we did a patent of directly driving the gate of the D-mode technology. So what those two benefits give us? So first of all, D-mode technology gives us the most robust solution for traction inverters. It gives us a low-cost process and reduce, of course, the system cost that I mentioned previously. High threshold voltage, which is important for the design rules of inverter applications. And the direct drive, when we are talking about inverter application, high current, we must parallel devices. So paralleling is easy when you can drive the gate directly using VisIC technology. And of course, we are eliminating the MOSFET switching because it is only when we are turning the device on. So it has best figure of merit of microjoule multiplied by resistance. In VisIC, we are supporting our market and our customers with various solutions. You can see here discrete devices that we are supporting, and also dies for customers who would like to build their own modules and their own discrete devices, but we're also supporting our customers with modules solutions as well, going to 600 amp as a technology validation and module development of our next generation solution, which is already transfer molded solutions, going from 300 amp to 400 amp solutions. Those are fits into two main types of applications that I mentioned, onboard chargers and inverters. So the V22, our 22 milliohm device, is suitable for PFC in onboard charger application when you don't have to parallel the devices. V60, a 60 milliohm device, which is suitable for DC to DC. For inverter applications, for low power applications, we can use still discrete devices in order to be much more optimized for the specific power rating, and moving to a very low resistance solution like the 4 milliohm and the 7 milliohm dies and the modules that we have. So to summarize, reliability is important for those technologies when we are talking about automotive traction, and it goes even beyond the Q101 qualification. Reliability is important, and I show you several slides about reliability and performance that we did, and not just us, but CPACE. And reduce the losses over the driving cycle. It's a key element, reducing in order to reduce the car cost. Thank you.